So let me start today. So suppose what I am trying to do first, let me explain. Suppose you are given two field extensions. Suppose L is the top one, which is extension over K, and F is and K is an extension of the base field F. So you can think that F is also an L is also an extension of F, the ground field. So there exists some degree of extension because I can consider K as a vector space over F. And suppose this be M, or suppose this be N, and for this I can consider, suppose this is M, then what is the total degree of extension? Total is the multiplication. That we will show. I mean the vector space dimension of the lowest field, the vector space dimension of the highest field with respect to the lowest field is the multiplication of this. Okay, multiplication of this extension and this extension. The multiplication of what? Multiplication of extension. That means the vector space's dimensions. Let there are two extensions. First one is K over F. And second one is L over K. Okay. Then field extension means we can talk about the degree of extension. Then L over F is multiplying. That is the vector space dimension multiplication. This K and this K are same. Okay. Don't get confused. Okay. So let me draw the picture. It is F is K is L. What is the picture? Let me draw it perfectly. Sorry. Okay, I think you will get it. Okay, and obviously we need to show that if also they need not be finite. There might be one that be one. Sorry, vector space dimension need not be finite every time. Even if the, for example, the ring extension itself is sometime is not finite. For example, if you consider the polynomial ring over the base ring, then there are infinitely many infinite bases. Or I mean, consider fx as vector space over A. Then there are infinitely many bases. Sorry, 1x, x squared, x cubed. Okay, infinite. So one thing must be infinite. Might be. If this is infinite, then at least one of them is infinite. Okay, and conversely, if this thing, one of this thing is infinite, then this is also infinite. This also you need to solve. Side is finite. Other side means either left hand side or right hand side I am talking about. Let me start the proof first. So first do the finite cases. Then I will look what about the infinite. Infinite case is not hard to prove. So first emphasize on the finite cases here. Okay. First of all, so let me assume this is something, and we will show that there is the product of this and this. Suppose L over K, it is M, and K over F, this is N, where M and N both finite. So let us assume what could be the basis. So let alpha 1 to basis for the extension. So it is M, so L over K, and let beta N basis for the extension K. Okay. I will show that the vector space basis of L over F is all types of alpha I beta j, where I equal to 1 to n, j equal to 1. So 1 or m or n, so whatever is. Alpha is from n, and yeah. So all types of this thing will be basis. I will show. Okay. So any element, say L belongs to L, can be written as a linear combination of these things over K. Sorry, over K. Written as, sorry, because it is vector space, so linear combination of basis element. I am considering first this thing, L over K. So there are bases, so the K linear combination of the basis element is L equal to alpha. Suppose it is, so scalars, let me take scalars, alpha O1, A1, alpha 1. Okay, let me write here. L equal to A1 alpha 1 plus A2 alpha 2 plus dot plus A M alpha M. Where from the scalars I am taking? So I am considering this extension. I am considering this extension. So the scalars must be from K. AI, I mean I equal to what? Dot M. That belongs to K. But any element of K is F linear combination of basis. So as soon as I get the elements inside K, consider this extension now. So this AI, it belongs for example, this belongs to K. Okay. But then AI can be written, for example, A1. A1 can be written as beta 1 into some scalars. Okay. Beta beta 1 into some scalars plus beta 2 into some scalars. That basis element plus dot 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 plus beta m into some scalars by the basis definition of the vector spaces basis. So I can write alpha 1 as what I can write alpha 1 as, suppose I can write this as beta 1 1 beta 1 plus beta 1 b1 to beta 2 plus dot 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 plus b 1. Suppose I am naming them as beta. There are n na beta runs from n, yeah. So suppose this is beta n. So I can also write a2 in this manner. Beta, beta. So I can write everything, and the last equation will be a is from m. A m equal to beta m1 beta 1 beta m2 beta 2 plus b m beta. Now put these values of these things a1 a2 and am whatever they are in here. Oh, just to mention, where beta ij, okay, beta ij, where I runs from 1 to I is the first index, so 1 to m, and j runs from the second index. It ran from 1 to n. All belongs to f because I took the f linear combinations here. So scalars will be from f. Understand? So let me put all things in the first equation. Then equal to, what is the value of a? A1. A1 is this thing. This is plus. So I'm writing the last term, okay? Because same thing I will repeatedly writing here. Plus beta into plus dot 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 plus beta n. That means it can be written as I equal to 1 to, so it can be written as beta ij alpha I beta j, where j equal I equal to 1 to m, j equal to 1 to n. That means, implies that, so how many elements are in the basis in this span? There are mn types of things in this total summation. Okay. Now I need to show that. No need to write here. Now if I can show, so acha, implies that L is span of alpha I bj, where I equal to 1 to m, j equal to 1 to n over. So I can show that the multiplication, the span, this is if this, so that was my tower. If this is generated by n element and this is generated by m element or something like that, then L is already spanned by the multiplication mn. So spanning set much I can show. Now I need to show that they are linearly independent. So if they are spanning set and they are the linearly independent, then we are done. Okay, observe that these are from F. I wrote it. So it is F linear combination. Now we want to check. We want to show. We want to show that the set is linearly dependent over it. So let us consider the same equation of scalars. So beta, let us take beta ij as scalars. No problem. Let us consider the relation. What relation? Or you can take Cij. If you already use Bij, you can use Cij, no problem. So I will write this form, okay? Cij alpha I beta j equal to 0, where I runs from 1 to m, j runs from 1 to. There is kind of double summation, okay? Summation on more indices. See, now, okay, that Cij equal to all types of Cij, that means. So we are considering that now see that. Okay. Let me again writing the same thing. Let me again write, which implies that now what is the coefficient of alpha 1 here? Alpha 1 coefficient is C 1 beta 1 plus C 1 n beta n. So beta was still m, right? M or n? N. Yes. This is the coefficient of alpha 1. What is the coefficient of alpha 2? Just unwrapping. Lastly, what is the coefficient of alpha n? Alpha is m, okay. Agree? Suppose take any element. I will show, first I will show these things are zero, the coefficients are zero. Every coefficient is zero. Suppose, okay. Now see, observe that things C11 beta 1 plus dot 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 plus C1 and beta n that belongs to L, because I considered beta 1 beta 2 be the elements of sorry K, and then that equation turns into linear independency of of K over L. But they alpha 2, so whenever I C11 are from F, whenever I am multiplying an element from K, that thing goes inside K. Similarly, this thing goes inside K. So plus these things, it also goes inside K. Similarly, this term, the whole thing goes inside K. Similarly, these bracketed terms, the coefficients coming from K. But these things are elements of L, the top field. So now the question is, this is another equation of dependency. So you can take it is d1, so it is suppose d1 alpha 1 plus d2 alpha 2 plus d dot 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 plus dm alpha m, where d1 is this thing, d2 is this thing, dm is this thing. Okay, but we know that alpha to alpha n, alpha 1 to alpha m, they are the basis of L over K. So that means d1, whatever we wrote to dm, that is 0. That means this is 0, this is 0, this is 0. So I can write is, in general, I can write, so it is, I can write at, instead of 1 1, each I equal to 1 I 1. I am not writing repeatedly, I will write in short notation. But this is so, which implies, as I explained, these things are 0. Every relation. 0. But it is 0 of which field? It is 0 of F. 0 of, I think, K. In which field the phenomenon is occurring, just look at the thing. It is 0 of L. Okay? So what does it mean? It means that every equation is, such equation is 0. For example, C11 beta 1 plus. What does this mean? That means everything is zero. C1 beta 2 plus C1 beta n is zero. C21 beta 1 plus C22 beta 2 plus C2. That is zero. In this way, Cn1 beta 1 C into n1 and C 1 minute 1 n. Am I writing? Oh, sorry. Yes, that is the problem. So C11, Cm1 will be there, right? Cm1, Cm1. That is zero. That means. Okay. Now, again, now these things are coming from the lower field, like lowest field, base field. And beta 1, beta 2, these are basis over k. This is basis of k over f. So from this equation, this is the linearly dependency equation. I must have this is zero. Again, since then we must have this thing is zero, this thing is zero. So I1, 1, 2, C, N, that is zero. Or fine. So you are done. So what we showed that C I1 is zero, that means for each I. So if I take I equal to 1, then C11, this part is zero. If I take C2, C I equal to 2, then this part, then this is zero. If I take I equal to m, then we will get this thing, the coefficient of beta 2 here, Cm2, this thing, everything is zero. So I get every coefficient as every Cij is at zero. That is Cij I equal to 1 to dot n, j equal to dot n. That's zeros. Zeros of which the lowest key. What? I mean, zeros of L here. I am writing zero only. So that is proved. So alpha and beta is a linearly independent because we started with this. We started with this relation. It is a long equation. This plus this. And my target was to show these as zeros. And I showed this as zero. So they are linearly independent. The set is linearly independent. Just linearly independent. L over, sorry. over the ground field was F, base field. The lowest field was F. So they are so it acts as a basis. Thus, thus for the extension, what is the extension? The extension is L over F, right? So what is the how many elements are there? There are mn elements. Hence, M is what? M was what? M was this, and N was this. This. Okay. I'm right. Finite case is done. I two M and N both are finite. So now one side is infinite case is to be done. It is remaining here. So first suppose that oh, first suppose that left hand side is infinite. Just let me show that what was the I need to prove? Yeah, I need to prove this thing. Yeah. So first I assume that either this or this is infinite. Right hand one of the term in the right hand side is infinite. I will show that this is infinite. That means there are infinite number of basis element which spans L over F. Now suppose that first suppose that this is L. So what is does mean by infinite? So there are infinite number of elements spans a vector space. Okay. See, A was the middle one, right? So oh sorry, it is L. So it is L. It's A. But this, if you act F as scalar, K needs infinite number of elements. L is again a bigger field of K, might be equal. Then it also needs so it needs much more element than K to span L. K, if at least K equal to L, at this is the least possibility, then still it needs infinite number of elements. And if it's much bigger than L, then more than infinity. So it is again infinity because it is a superfield. So subfield of L. Finite number of linearly independent. Okay, that is the main crux. Because in infinite means if you treat any element as a basis, then that will. But they are the basis element. So in a vector space dimension, basis element or linearly independent. Right, number. Independent elements. A L. There are infinite number of linearly independent elements of K which spans K is a vector space over L. But K is a subfield of L. So these linearly independent elements are much needed. Extra some element is needed, but this number of linearly independent elements is already infinite. So this mm, bare minimum, infinitely minimum element must exist in any basis. Because any basis have same cardinality. So if you take any other basis, that basis will also be infinitely number of elements of K over L, of K over F. But K is a subfield of L. So, so, so one thing is done. When now what happens if L over K is infinite? I assume first this is infinite. This infinite implies this equal to infinite. Now I will assume this is infinite. I need to show this is infinite. Next. Does assume that what is L over F. So what K over F. So L over K. What happens if this is infinite? So by definition, then there are infinite number of linearly that means the basis elements independent elements L over K which spans L as a vector space over L vector space over K. So what can I say about that? What can I say about the lower extension? That is I have assumed this is infinite extension. Then that must be infinite. Why that must be infinite? Because if this is finite, because if this is finite, then suppose it is finite, generated by alpha 1 to some alpha k, then that set can act as a basis of this, because this belongs to L. Okay, but if it's generated as a finite extension of this thing, finite extension of these things, these things can also be generated finitely as this extension. Okay, again I am saying, if if this is finite, I mean, you can write L equal to some C1 or alpha 1 plus C k alpha k, then you can treat this Ci's as element of K, because if Ci was initially to be belongs to A, but it is F. So I can write every element as a linear combination, as a K linear combination of these things. So that means these things are finite. But I assume this is infinite, so this must be infinite. Otherwise, there will be a contradiction. What I explained. So again, now lastly, assume that assume that this is infinite. I need to show either this or this is infinite. But whatever we showed already, if these things are finite, then this thing is finite by this thing. Whatever we did, if these and these are finite, then this is finite. So by taking contrapositive, if this is infinite, either one of them is infinite. Lastly, assume that then at least must finite. Otherwise, because if I assume that this is finite and this is finite, suppose this is equal to m, this is m, then we can prove that this thing is mn, which is a finite number. So if this is infinite, so either this or this will be infinite. So our so root. So that is the main theorem. Okay. Just a minute. So, as a corollary, I can say that immediate corollary. Okay. Suppose L over a finite extension. Let K lies inside L and F. I mean, in the middle of the tower, and let K be inside. That means K over F is an extension, and L over K is an extension. Mhm. I mean that is. Now I can say then if right. Okay. So this the largest tower. So this is finite means both are finite. Okay. This finite means this is also finite. Because if this is infinite, then one of them must be infinite. So this is finite means L over F is finite means K over F is also finite. Because if K over F is infinite, then that is infinite. So divisibility takes place. Proof. Then because if that doesn't happen, K over F is infinite, then L over L becomes infinite. Contradiction. Now the from the formula or equation, whatever you prefer, L over F equal to K over F. Uh, so this term is K over F is something in some L over F is this into something. That means both are integer. So this thing divides this thing. And what is the quotient? Quotient is this thing. After dividing, we will get this. We are done. Just I will give you 1 minute, 1 or 1.5 minutes to go through this. Then I will continue. Okay. So let me proceed. Still good. Example. So take consider extensions. You okay. We consider and need not be you. Consider the extension. First consider the extension. So what is the degree of extension? It is alpha is root 2. Q is x. This degree of this, right? Degree of minimal polynomial. So degree of this. That means consequently I am saying so to prove it is minimal polynomial, then you can show that root that satisfies this and that is a minimal degree. Why? Because it is irreducible. If it is reducible, then it is not minimal. I can then cut down the degree by reducing and whichever the smaller and take the smaller part. Again, if it is reducible, then again cut down the degree. So irreducible means that scene doesn't occur. What is the degree of polynomial? It is 6. Also, consider u square. Mhm. That is degree 2 because the minimal polynomial is x square minus 2, which implies then I can consider the degree. What is this? What is this? This is by our previous formula. This is this thing. This is divided by this. That means this is 3. 6 by 2 is 3. That means this is 6 by 2, which is 3. So the utility of this thing is I don't need to determine the minimal polynomial. This is the vector space dimension. First of all, this is the vector space dimension, which is again as minimal polynomial degree of minimal polynomial, which is exactly equal to this. So whichever is easier between this, and this, we will be using this. But see the vector space, I need to calculate what is the vector space dimension, which is pretty laborious. If we need to consider what is the um, minimal polynomial of this thing over this, then that is again hard, difficult to calculate. So the easiest thing is this. We can avoid the minimal polynomial thing. If in the exam you are asked to calculate by minimal polynomial, then you will use. But if you asked to calculate what is this, then I can use this. That is the facility or advantage of this. So this shows that the minimal polynomial of C root 2 over u root 2 x this of 3. Because again, because it is the degree of this thing, degree of this element. 6. It is not 6 into root 2, 6th root of 2. Degree of m of this, calculating that is. So by for your own interest, you can think what could be the minimal polynomial of this thing. What is exactly the minimal polynomial? Because 2 to the power, if I take x equal to 2 to the power 1 by 6, then 2 to the power 1 by 2 is available. So x cube equal to 2 to the power 1 by 2. That is square root of 2. That means x cube minus 2 equal to 0. Oh, sorry, square root 2 is 0. So this is a probable candidate. This is a possible candidate because this is degree 3 polynomial, minimal polynomial ka degree 3, and that will be trivial. You need not to be check irreducible because it is any polynomial. We proved in the previous class that if any polynomial that divides this thing is divisible by minimal polynomial, and minimal polynomial ka degree is 3, and minimal polynomial is unique. So this is the minimal polynomial. Okay. So that much I will stop there.